So let me share. So you know how many people are going to show up today. Maybe what I'll do then is make it interactive. So you ask, don't be shy of asking any questions. Okay?
Okay, sir.
Be loud today. Okay, so I should. Yeah, so we were discussing, as you know, and late in the last class. Oh, someone else. Someone.
Hello.
Added. Hi, Diganta.
Hi, sir.
We only have Anleap today. Yeah, so I'm going to make. I've asked her to yell and scream as much as.
Yeah. So I don't know if anybody else is coming, but people were getting some weird issues. So specifically, Harsh was getting some weird issues with this the code for the last CBMC problem.
No, weird issues with what?
With this last CBMC assignments code that you had shared.
How many people have submitted? I know Anli hasn't submitted. She said that I'm encouraging her to submit because she has some exams, etc. this week. And so even if it's late.
I'll check how many people have submitted.
Huh?
Let me see. I think 4 people have submitted.
Let's see. So there are, how many people have registered for the course? I mean, other than Anli, only 4, no? Or 5?
I don't know, sir. I don't.
No, I have. I think it's, let's see, Harsh.
Harsh has. Chandradeep.
Harsh, Chandradeep, Siddhant. Dhruv.
That's 4.
And Sayak has registered too, so I don't know what that means. So and Anli, okay, with Anli, by you're actually officially kind of cross-registered, isn't it, Anli?
Yes, sir.
Yeah, which means you will have to. Dhruv is here, but. Yeah, so which means you will have to then, in that case, I mean, you will have to get a grade also, correct, from here?
Yes, sir. Yes, sir.
Which means then you have to submit. Okay, even if it's late, that's okay. Okay, we'll try to submit it as quickly. So Dhruv have submitted. The other 4 have submitted. That's good. I think you should get cracking on grading them. Okay.
Yeah, sure.
Till the end, and we will discuss that later on. So, so let's see.
Yeah. Okay. So there was some issue which Harsh was facing. I was hoping that he would be here, but I think he is not here yet.
Why is it that so late?
Yeah,
it's been. I mean, no.
but
I guess it's better late than ever. Okay. What is the issue?
Yeah, so he tried running some code like this particular code that you had sent, and then in the output CBMC.
No, but he has already submitted the CBMC assignment. He did not have any issue running those problems. Correct?
Yeah, no. So the issue was not such that he could not submit. I think So nonetheless, he did submit, but CBMC was outputting the array in a very weird way. So even with the assumption that the array length is within 4, it was also still giving us some really huge
maybe
array elements values.
He's not here today. So what should?
Yeah, maybe we should discuss this later on this year.
Yeah, so maybe so I'm also kind of cheating and taking what is actually meant to be tutorials for regular lectures, which is a bad thing on my part. So today, since there are people here and I'm here, I will do it. And probably the last thing which I was going to introduce, maybe I'll wait till tomorrow. Okay. So let's open this for. I don't know. Andeep has not submitted the CBMC assignment, so you should take this opportunity, Andeep, to ask questions and what the issues that you have and so on. I mean, even if you don't want to do in this, you should take, indulge. Okay. So let's, since we're here, and since I'm here, so let's do it. Okay, so last time we spent quite a bit of time in looking at how SSA is generated, okay, specifically how CBMC generates, okay. And so far we have discussed bounded model checking, and we were looking at how to implement bounded model checking so roughly we have discussed in kind of three different ways. Now, I think the problem one here, we quickly summarize. Problem one is intended for you to get acquainted with using the transition system model to do the bounded model checking verification. Okay, so here in this example, using PC, that's how we did. Okay, to model the behavior of this as a formula, and that's what this transition says. And here we want you to encode this verification condition for unwinding this transition relation, for to check if there are no k-long error. Okay. For this particular property that we have under this assumption. So I did discuss in one of the classes the BMC formula, but just to make sure that that you understand, you know what I mean by a BMC formula. And to construct a BMC formula with using this transition relation that's shown here as unwinding that transition relation.
So the symbolic formulas we learned last time.
Correct. What is that? Can you prompt me?
So every statement we write in terms of symbols, and every statement is run as a formula itself.
Yeah, but I think you're referring to the SSA version. Okay, so this relation here that I've shown here as TS, okay, on the right side.
Yes, sir.
Now that is a relation that relates a particular pre-state to a post-state after I execute the program. Okay, so in this transition system model, what is your so this says, what does it say? So it has two components, by the way. There is an initial condition. Okay, that's what I represents here. Yeah, so what does that say? That says, oh, I'm at the entry point. Okay, to begin with, I'm at the entry point. That means that PC is equal to 0, and whatever my initial assumption holds. Okay, that is the initial predicate. Okay, and after that, it defines the one step, the effect of executing one arbitrary step in the program, and that is stated as a relation between a pre-state and a post-state. And each state has three components here: PC, X, and Y. Okay, and the primed version of the same is assumed to be where S0, what I call as S0 here, is really a triple. Okay, each SI here is actually a triple. PC of I, X of I, and Y of, there's a Y here as well. Yeah, Y of I. Okay. And this is stated in a general fashion. PC is equal to a 0. Somebody else has joined. Harsh here. So maybe
yes, sorry, I'm late.
no, that's okay. So yeah. So let me go through this part, okay, and then maybe we can even discuss after I do it, because I decided not to maybe discuss if the other two are not going to join today. Then I will defer the discussion of the introducing fixed points, etc. The discussion prelude to that till next time. So here we are discussing the transition system model for the program, which I've already gone through. So it relates, an S to, it's stated in terms of S and S prime, okay? In terms of S and S prime here, okay? And similarly, you have S prime. So it says that if I'm, the primed version is the next state that resolves. And so it says that if in the current state, I'm at location 0, then I have to execute the instruction at location 0, at program counter location 0, and that is the effect of executing. That is what is stated as a relation between I prime and between the primed versions and the unprimed in terms of the unprimed version. Is that what you meant, Anli, when you said that? Okay, but so it just says what the effect of executing one step of the program is, and the program could be in any one of the PC location, and at the entry point it will be at the PC will be 0, and that's how. And it's in that sense that this transition relation, which is described, here, it models the effect of executing one step of the program by relating the pre-state to the post state. Now, in bounded model checking, what we'll have to check is that we have to we have to model the effect of running this program for K steps, okay? K steps starting from an initial state. And that's the question that I was asking, okay? Now that I've described this transition system, that is one way to if you're modeling your program as transition system, that's one way to model. So this question, this particular problem asks you to formulate this BMC formula, which I've already shown in one of the previous classes, but I will refresh the thing. Harsh, now that with that introduction, Harsh, how will you denote the a formula that captures the effect of executing K steps?
Like what? For?
In terms of the transition relation. Or let me, yeah. I guess you,
like for this problem one, right?
Yeah, this particular problem. Yeah. I mean, you could, yeah.
So what do I have? Could you repeat the question? What did I have to do?
What is, I want you to hear, the problem is, I mean, I'm trying to assist you. I mean, you have to go home and then work the thing. So,
Yeah,
but, so what I'm saying is, if you want to, let's suppose, okay, well, let me ask, let me put it this way. What does this do? Okay, what does this represent? Okay, I say I of S naughts, where each one, see if I'm in S naught, okay, which is really like PC naught, X naught, Y naught, and So if I have this is a formula, right?
Right.
Okay. What does this represent? What any satisfying instance of this formula, what does it represent? What does it give you?
Like any satisfying instant would give us like for what values of this would it satisfy, right?
Correct.
Yeah.
So it will give you, so this has how many variables? It has, this is what I call as S0, this triple, and this is, I'm sorry, this is, I didn't type it correctly. Okay. So I'm instantiating the transition relation with this. Okay. Okay. See, any instantiation. So this is a formula over how many variables? How many variables does it have?
Yeah, 3 for like PC0, X0, and Y0.
And PC1, X1, and Y.
Oh yeah, and PC1, X1, Y1, yes.
So there's six variables.
Mm-hmm.
Okay.
Correct.
So 3 of them form the as part of the state S0. The other 3 is S1. Okay. So anything that satisfies, makes this formula true, should be some an S0, okay, where it satisfies the initial condition I.
Mm-hmm.
Okay.
Right.
Okay. So which says, what does the initial condition say? That I'm at the entry point. I'm at PC0.
Right.
And whatever the value of X and Y, the initial value should be
less than equal to.
Yeah. So it would be some state, okay,
Mm-hmm.
which is one of the initial states. Okay. And then it has to, this formula also has to satisfy the transition relation, which captures the one-step effect of executing an arbitrary step. Okay.
Correct. Yes.
So what is that? What is that? What does that say? So it says,
yeah, like I equal to whatever.
yeah. So it'll, yeah. If since I am in an initial state, okay. So I am in PC0. Okay. So PC0 is PC0. PC is equal to 0. And I know that, X0 and Y0 satisfy this assumption, the absolute, X minus Y, the abs is less than or equal to 2. And anything that, any value PC1, X1, and Y1 can take to that will make this formula satisfy will be whatever state that you get after executing one step in your program, which happens to be the instruction at I is equal to 0.
I equal to 0, yes.
Okay. So in that sense, this captures the, it captures this all possible ways, okay, of one, an execution trace that is one long, okay, correct? If I'm in S0, a legal execution of this program, okay, starting from I and then doing one step, okay.
Oh, yeah.
So that's what this thing is. So now if you want to, now I'll ask, okay. So this, so I'm asking you to make a formula that'll encode the all execution traces of that originate from any initial state up to, that is K long. Okay.
Okay.
So if I did the same thing here.
But K long, you mean K steps of execution?
Yeah, K steps. Okay, 2 steps means I'll have to. Now, if I did, so if I did another conjunction here, okay,
You would just add the third line of code.
Yeah, but no. The third line is automatically is automatically done. So all I need to do is to chain it through like this.
Mm-hmm.
Okay.
Yes.
Now this will be S0, where S0 is PC naught X naught Y naught. So this will encode any satisfying instance of that formula will be an instance of an execution, but that is
K.
3 steps long.
3 steps, yes. Yeah.
Okay.
Correct.
Now do you get it, Anli?
Yes, sir.
So that is what I wanted. Okay. So I'm Dhruv. I guess you understand this because you've already seen a version of this before. Or do you have any questions? Do you understand?
No, I don't have any questions.
Yeah. So here what I'm saying is for some K, what would it be? Which has to be parameterized as K. So it has to be just ... I mean, obviously this formula has to be finite, but if you kind of abuse the notation that we do, then it will be TS with SK minus 1, SK. Okay. Of course, in order for this to be a particular formula, you will have to instantiate it for particular K. Okay. So this formula then, it's a symbolic formula, Anli, that as you said, but it is modeling what? It is characterizing all execution traces that are legal execution traces that start from any one of the initial states, okay, and runs K steps. Correct? Yes, say yes or no.
Yes, sir. Yes, sir.
Yeah. Okay. Since we can't see each other's face, I think you have to be expressive. I'd like you to be. So now, suppose now I want to, how will you model this particular property? I want to check that X is equal to Y holds good. When I exit the program, okay? That I want to now. This is modeling all execution traces that are up to up to K long. Okay, up to that's the K long. Now I want to check that what are the different ways in which I can get out of this program, exit this program and get to line 5. So if I'm at line 5, whenever I'm at line 5, I want to check that X is equal to Y. Okay. So how will you model this property? I can get to this point how? I can get out. I can exit after 0 iteration, or I can exit after 1 iteration and after 2 iteration and so on, correct? So the property that I want to check itself generically is, if I call it prop, that is once again stated as a predicate of S, is modeled as what? If my PC is 5, okay, once again, my state has 3 components. What are the 3 components, Andli?
PC4.
No. First, generically, no matter where I am. Okay, so it is PC, X, and Y. It has 3 components, right?
Yes, sir.
So I'm just stating an arbitrary predicate. So if I'm at PC 5, if PC is 5, okay, I'm using lowercase, then X must be equal to Y. Okay, that's what I want to check. Now, since I don't know what the initial value of X and Y are. So I know that I is equal to 0, okay? But potentially I can get out, I can exit and get here to PC5 after 0 iteration, 1 iteration, 2 iteration, and so on. If my idea is to check for this property of, is not violated after up to k steps, okay? Then what do I have to verify? Okay, for simplicity, I'll name this as P rather than prop. Then, like what you were saying, Andeep, so first I have to check that it is, I could, starting with this initial state, I can get out, if, this itself, I mean, without executing any, starting with the initial state itself, okay? So, if my, but I want to verify only when PC is equal to 5. So first I have to make sure that it is not violated in the initial state. It is not violated after I take 1 step, because there's potentially I can reach location 5, okay, after 1 step, and after 2 steps and 3 steps, and this I want to check after k steps, and therefore what I'll have to do this is, okay, this is one part of my formula. This is the VC, the BMC, what I'm saying here. I'm defining this, okay? What this says is, for any execution that is a trace, a legal, valid executions that I can get starting from an initial condition, okay? And what I'll have to check that this property is not violated in the initial state, nor in the state that I get after executing 1 step, 2 step, or 2 step, or 3 steps, and so on. So that I can check by saying that so negation of P. I mean, this BMC formula that I'm asking is, it actually checks that if the property will ever get violated, with that it never gets violated up to k steps. So I can, if I do something like this, okay, that of S naught, or okay. So if if this becomes ever true for any instance, then what does this mean, Dhruv? So there are 2 parts here. One is that I have a legal execution, and this one checks that P, the property P could potentially be violated in initial state, or after maybe after I execute 1 step, and potentially reach P5 and so on. So so any satisfying instance of this, what does it say? Dhruv, are you there? Harsh, are you guys there?
Yes, sir, I'm there.
Maybe Dhruv left. Oh, but he's muted. So if this gets satisfied,
He said in the comments, network problem. I'm sorry.
Okay. So then potentially it is violated in any one of either in the kth step, first step, and so on up to k. Okay. So if there is a satisfying instance of it, then these parts have to be true. So it has to be a legal execution of up to k steps. And then I'm checking that if there is any state between, that I get after executing first, zero step, one step, two step, and so on. Okay. So in effect, if there is a satisfying instance, it will also has to make the second part true. Okay. And second part true, which will be true when? Only when either P is violated in the initial state itself, or after I execute one step, two step, etc. Okay.
So when we say one step, does it mean one statement?
Yeah, it does state that the effect you execute whatever that statement, one statement that is at whatever the value of PC is. Okay, that's what it says. Okay, so can it ever can it ever get violated in the initial state, Harsh? Although I have put this thing in here.
Yeah, sir, could you repeat the question? Like,
can this ever get violated? Can P of S naught be false in the initial state I?
like if the initial state, if the initial state is no, it can't be false, right? Because you won't be able to, like that is our assumption, like some sense. So it can't be false.
No, the property just says if X is equal to Y. I haven't made the assumption that X is equal to Y in the initial state. I only made that X minus Y must be less than or equal to 2.
Yeah, no, like the question was like, can the initial condition be false?
No, that's not my question. Can P of S naught, as I've defined here, okay?
Oh, okay.
Be ever false? When can this be false in the initial state? I mean, this can be, this can get satisfied if indeed I have, there's an initial state and in which P is violated, right?
Wait. Yeah, okay. Oh.
Why can't this be violated in the initial state? Because what does the initial state say?
If
I'm at in this state, the P definition of P says if my PC is, if I'm at location 5, then X must be equal to Y.
Okay, yeah.
So, but when in the initial any state that satisfies the initial condition, what is the PC?
Okay, yeah, like S naught, it can't be false, right? Because at S naught, PC is not 5, right?
That is right. Okay, that is what I wanted. As a matter of X equal to Y can be violated, but PC can never be 5. Okay, because I'm not even at this location. Okay, so this property says that X is equal to Y needs to be checked only if ever that if I'm at PC location PC is equal to 5, and that's what this is checking. Okay, this is checking my S0, S1, S2, etc. Sk have to be, S0 state has to be whatever is the initial, something that satisfies the initial condition. S1 has to be something that is produced after I execute one step of my program. But what step what instruction I execute in the program depends on whatever is the PC in that state. Okay, that's what it is saying. Okay, so what Anleep said was correct. It is each transition relation is stating the effect of one thing. That's why. So after I can never get to PC5. Okay, if I'm at location 0. Therefore, P cannot be violated. Of course, after executing one step here, can it be violated? Okay, so so I'm asking the same question. After executing one step of your program, okay, say in S1, can it be violated?
No, not even like, yeah. Am I supposed to answer, right?
Yeah, please.
Yeah, and like it can't be violated in S1 as well because same reason, right? PC is not 5.
Yeah, but what am I saying? Say after one step, if I'm at PC is equal to 0, what is the next step that I get? I will.
Yeah, we get that.
So it cannot be because I'm at PC1. Okay.
Yeah.
So I'll move from 0 to 1. And for the same reason as you did, it cannot be violated in S1. Okay. But now, then when I go from 1 to 2 in the second step, not the 0th step, first step, second step. The second step, that is in state S2, okay, PC2, X2, Y2. In that state, can it be violated, Anleep?
No, sir.
Why
because
not?
I has a I less than or equal 10.
Correct, exactly right. So you're right. Okay, so because of this condition, okay, that I is never, I is equal to 0. Therefore, I won't get to PC5. Now, if I had not initialized this I is equal to 0 in step 0, then I could have got. Okay. But this one is checking. He doesn't know. So I'm modeling it in such a way that I'll assume that it just may be possible. Okay. In this particular example, it is not possible. But this formula that I have encoded here cannot be, this works for any transition system, any initial condition. Okay. So that's why it is a generic formula. That's why it's a generic BMC formula. And I could use this. So here I can plug in any transition system TS, for a program. I mean, that corresponds to program in any initial condition, and it still works. Okay, so that's why it's here. It does not. Let's suppose that I did not have this statement. Okay, if my program did not have this statement at 0. I mean, there is no. I had not initialized I, and I allow. It may be crazy. But say I'll assume that I can be anything, some legal value. Then in step, after step 2, in step 2, I could get out, correct? I can, and potentially, then there is a possibility, okay? So in this case, what will happen is, until K is, because the program, the while loop is such that you only exit after 10 iterations. Therefore, this one, will never get to this, location 5. So for K less than or equal to 10, less than 10, okay, it will never reach P, and therefore it never gets violated. It gets interesting only for K greater than or equal to 10. Greater than or equal to 10, then you can where you can get. Okay, so that is good. So that is what the intention of this problem was. Yeah. Okay. So what you're required to do now, I hope you understand. See here, I'm using a different model. I mean, we also saw how to model this, program in terms of SSA. And but just for instructive purposes, I'm making you do this, okay? And what I want you to do is to encode for any particular k. Okay, actually I said k is equal to 3. I'll change, because for k, I mean, you could do for k is equal to 3. I mean, I've already shown you this one. Do up to k is equal to 10, or more, and run it. Okay. The reason that this kind of modeling is not used for software, rather, we've spent a great deal of time in looking at SSA. The reason that this one is not used is because this way of modeling, firstly, it adds the PC as a component state. Therefore, it just multiplies the number of states that you get if you used only the program variables. But more importantly, it unnecessarily explores, there are so many false paths in here. You know that if you're mostly, if you're in PC1, you only get there. And then if you're in PC1, once you're in the loop, if you're at PC2, you only get to PC3, PC4, and so on. So even in those cases, there are so many false paths that are encoded in here. So when you try to, when you ship this to a SAT formula, it unnecessarily, the idea is, if there is a satisfying instance for this BMC formula, that would mean there is a bug. Okay. In doing so, it unnecessarily maybe end up exploring those paths, values of PCs that are obviously not possible for this program. This is generally true for programs. Okay, whereas for hardware, etc., it is not the case. So since the CFG is kind of not taken into account, and it may be more efficient to eliminate those paths that are syntactically not feasible, and that's why that was the motivation for doing SSA. But for instructive purposes, I'm also having you to do this, and it's only for large formulas that you may find the SSA formalism more efficient than this one, for the reason that I just now described. And that is the purpose of this this particular problem. That's why I wanted you to try time it out. So for very small k, there will not be any difference between SSA and this one. And even for a large k for this program, because the program is small, maybe you won't find any difference. But I thought you might as well do that exercise. Okay, good. So any questions there? So you understand what you need to do as for this experiment. I hope. Yeah, and whoever is here, Harsh.
Yes, sir.
You understand what needs to be done?
So I have a question. If
Yeah.
k is any number lesser than 10, so we never reach the state PC equal to 5.
Yeah, so it'll obviously be, it'll be unsat. This particular formula will be unsat. No. Yeah, so which means there is no bug. So this encodes the possibility of a bug. Okay, any satisfying instance of this will be, that there's a bug. So for k up to 10, up for less than 10, it will not. It should not. Okay. Unless your encoding is, you have something wrong in encoding, or I have made something, some mistake here. Okay, it should not. Correct. So that's why, I said try and do it for k greater than or equal to 10. So what will happen for k is equal to 10? This will get out and then comes by only exactly after 10 steps. If you run it for k values of k which is greater than greater than 10, what will it do? Actually, there is a what will it do? That's interesting. So, Harsh,
for I greater than 10.
No, I meant for k greater than 10. Okay.
Ah.
This formula is parameterized with respect to k. Okay. So if I run it for more than 10 steps,
Good
10
question.
symbolic steps.
Like for greater than 10, it should either like unwind the loop, I guess.
No.
No?
You're already unwinding the loop through this
Okay.
okay. But see, what will happen is after 10, your PC will be 5, okay? And you already see there is a little bit of a issue, okay? I never say what will happen. So this transition system relation that I've defined here, okay, is incomplete in some ways. It doesn't say what happens when I'm at 5, correct? So in order to really, so what it will say is at PC is equal to 5, it can be, if nothing is said, if PC is equal to 5, oh, the next state could be anything, okay? That's what it'll assume. So to make it complete, you will have to define. Okay, this is kind of the issue with this thing. So potentially there must be in my definition of S comma S prime that I had here, I should also have the thing. If PC is equal to 5, then I say, I'll stay at PC is equal to 5 because it's terminated, right? One way of kind of modeling it rather than leaving it open-ended, which means this TS can become true for whatever thing. So I'll say I'll remain at PC is equal to 5 and S will be equal to S prime, okay? So if I added this particular clause along with the rest of the thing, okay, the rest of the thing that you already have, if you added this, then it'll be interesting, okay? So even for, after you run it for more than anything that is more than 10, you will continue to stay at 5. Because if I'm PC at 5, I will continue to be at 5 and nothing changes, okay? And my state remains the same. I think then it would do something meaningful in the way that we want. Otherwise, I have left it kind of open-ended. So so this is what it would be. So that it was so you should try it. Now you have the benefit of knowing this one. When you try it without adding this one. Say check what happens if P gets violated after 10 steps, because here the transition relation, the way of defined in the slide, is incomplete. But then you also run it for K greater than some values for K greater than 10 with this conjunction added. So that way you have made the transition system somewhat true to what happens in this in a real program. When you reach the terminating state, you just stay there without changing anything. Then of course your property, if it wants to reach 5, if it ever did not get ever violated, then it has to continue to not get violated. Okay, so that's something you can check. Yeah. Okay, so I still have a little bit of 5-10 minutes, so I will not go to this. We have already kind of gone through. The purpose of this problem too was just for you to contrast. This is one method, okay, of bounded model checking using this is what I call as global transition system. Okay, you could unwind the transition system itself. Then we talked about, another way to do is through SSA. If you can model the program as SSA using timestamped variables, and we have spent a great deal of time in doing that. But once you represent them as SSA, there are two ways of doing it. One, you could enumerate all the paths through the CFG and then generate the SSA for individual parts, and then you will have to show that that if you for every part that you will have to do. Now, that is not a very efficient way to do at all, because we already observed that there are exponentially large number of parts, and you don't use that. Okay. Instead, you do something like this, and that's what CBMC does. Okay. So what it does is generates a merged SSA. It encodes the body of the loop as a merged SSA, and then generates the for each unwinding, it generates a formula, an SSA formula in terms of those many unwindings. Okay, so I'm going to so that is what I was discussing here. Okay, and this problem, I wanted you to what we had was, let me put this one. Okay, we had discussed these two things. Okay, as the result of unwinding, when you unwind, you can the result of unwinding a loop can be expressed as nested if then else. And I wanted you to use show VCCs to generate the VCC and review it. Okay, so that's what I showed, and we spent really time. So here there is one disadvantage. I mean, I don't know if either of you or people here ever got to. Is Dhruv back here? Is Dhruv back? Maybe he's still not back. Okay, so if he's not back, then either of you, Hirsch or Anlib, who are here, did you generating the VCC for these two programs?
Sir, I think I forgot to do it, but I can do it right now.
No. You don't. I asked you. Don't. The purpose is not to make you do it here. Okay. So if you had done it, then I would have, given your. I mean, asked your feedback. If you have not done it, is thing. I would still like you to do it, and contrast this. Okay. The SSA for this, when you generate it like this, to how it would do after you unwind and generate it. Okay. So that would be instructive. So and there are two ways. See here, when you do it, if CBMC did the unwinding like this, okay, where you unwound and then you can get out after one iteration, two iteration and so on. Then you check the property that you want to check at the exit of the loop. So you'll have as many asserts in here. So what CBMC does this way, if you were encoding your unwindings in this way and then generated the SSAs, the merged SSA, you would have to check one assertion for every one separate assertion for after every unwinding, because you want to, after 0, 1 second, and so on. And that is kind of not very efficient to do, okay? Because if for n unwindings, it will generate n different assertions. Instead, there is a trick that it can use, and that is what I want you to CBMC uses. It's somewhat of a clever trick. So so here is the, the result of K1 unwinding. So I'm going to put this thing here. Yeah. You see, what is the difference between here and here? This one and this one. Or maybe, you can do K is equal to 2. So here I'm doing 2 unwindings, and I'm checking after 1 unwinding, it's a second unwinding. So here, what I'm doing is, see, I could merge. I can do all the, in the way that I generate the merged SSA. So instead, I can just do this. So after, I do the first unwinding, the second unwinding, where I have put the body here. But else, since I'm only interested in up to 2 unwindings, then I don't do anything. I put else here. Now, I'll put an assume statement here. Okay, so to indicate that because I can get to in 2 unwindings, the only way I can get to the exit of the loop, if ever I exited either after 1 unwinding or after 2 unwinding. Since here I have merged those 2 things, and I'm also allowing the whole thing, allowing for other things. Either you have to catch by inserting the assertion right there, in which case you will assert VCCs for multiple assertions. Instead, I'm being here a bit clever. Okay, so here I say, now I will reach this assertion. I want to check only after, for 2 unwindings, I want to check only after 2 unwindings. Therefore, what are the ways I could generate? I could come here after 1 iteration. Either I is less than or equal to n is true, or after the second iteration, I plus 1, because I will be incremented by 1. I'll be doing, I'll be checking, I could be reaching this location after exiting after the second iteration, at which point this, exit condition will be in terms of I plus 1, whatever the value, the latest value at that time. This is the kind of thing that, so that way, what it is doing is that I am, letting it compute, get the actual values for 2 iterations. Otherwise, it'll just have whatever is after the second and third iteration. But I'm making an assumption that forces this assertion here to be checked either after exiting the first time or the second time. Okay, and that's how internally CBMC does. It does not do unroll the loops, do the unwinding in the way that I've shown here in terms of this code, but rather it does something like this. Okay, so where it puts empty statements after else's, and then puts forces an assumption which will make this point of the assertion reachable only if and only after 1 and 2. Now, so it will force it to check this assertion only in those 2 cases, which was being done here anyway, in 2 independent assertions, and that's what will happen. Okay, and that's the one that I'm illustrating here. And if you could contrast that with this thing. So what CBMC does is it's equivalent to generating, the SSA will be equivalent to generating for this code that I've shown here, but it does that internally, and that's what I've shown here. Yeah, so this is the SSA. If you use the thing, you would get this. Okay, and you can see here what it does is the SSA that it generates is for this for this program. Okay, something like this. Okay, I'm just going to put it here for your benefit. Okay. And you will see first it generates this. Yeah, so now I have the whole thing. So there are lots of guards it generates. Okay, guard 1 to denote this one. This is guard 2, which denotes this condition. Okay, and that's what guard 2 is. It's comparing X and Y. And guard 3, which is this condition instantiated on the new value after I is incremented. After I is incremented, it becomes 1. That's what this the guard 3 is. Okay, and then there is a guard 4 also generated right here. Right here, you see. Okay, and that checks if in the second iteration it has to check whether X is less than Y and so on. And then this assumption, it's although it is not explicit in the unwinding, it does it implicitly. It is assuming that I can reach. I want to check only after this assertion at the exit of the loop for the first 2 iterations, and that's why this it's making this assumption that either guard 1, which is the negation of guard 1, or or the negation of guard 2 is true. So that is the same as negation of guard 1 and guard 3. I'm sorry, guard 3 cannot be. The conjunction of that cannot be true. So this thing here is exactly doing it, but this is not being done. It's in the unwinding. It happens in CBMC automatically, and after that, it checks. It checks the assertion on the completely merged value, that whatever that you get. So because here I have closed both all the if then else's here, okay, before I get to this, and therefore it it uses it has 2 more merge points where it is used. But if you used the complete merge of thing, then you better ensure that you exit the loop only for first and second, because this is k is equal to 2, and that's what it does. And I want you to the purpose of this exercise is for you to try it on these things, okay? What I've shown here, okay? And I will update my assignment. I really want you to try it on this code, these 4 code, and also try it with generate the VCC after unwinding, and then review it, and then make sure that you understand. So I really want you to do it, because I don't want, maybe I'll put a deadline, and at least the next time when you're here next week, I would have liked for you to have done, made some things so that you could, give your feedback and whatever issues, etc. But otherwise, I'll be the one who will be talking, and it'll be a monologue, and I don't like that. Okay, I mean, that's not good for anyone. And so if you don't do what I even say, I mean, I'm using so much hand-holding here, and I'd appreciate that if you could follow through on what I have requested you to do, so that we can have some lively discussion. Otherwise, the kind of insight that you will get may not be as good. Okay, that's all I can say. Okay, any questions?
Sir, I have a question, but it's not related to this assignment, but it's related to CBMC. So one of the question was how do people in the real world scale this CBMC thing? Because I was trying to prove some stuff, but for n greater than, let's say you are doing something on array, and it hardly goes over n greater than 16 or something like that, 16, 17. So how, let's say I want to prove it for an arbitrary n. So how would I, or at least n for some higher number, So how would I go about doing that?
No. I think based on one isolated experiment, you should not come to the conclusion. The answer to that will be, based on, I haven't seen your example. What I can say is, although BMC is, and I think I don't have that one example that I will show you next time. So today, since I will answer your question in a little bit general fashion, before I will get to this. Bounded model checking is the most widely used among all model checking techniques. Okay, that too, bounded model checking based on SMT solvers is among all model checking methods. It is the most widely used in practice, which there I'm including industries as well. Okay, it is quite widely used in several industries. I can name Toyota. Lots of, especially in automotive industry. Okay, so it does scale up. I haven't looked at your example. Scaling is in general an issue for all verification methods. I will show you one example. Yes, if you try to unwind million times, okay, or you do something crazy. I don't know what exactly is happening. For 16 unwindings, it should not be an issue. Okay. Is what I'm saying. But maybe with arrays, it could be, okay. And maybe you will have to use certain tricks for, with arrays. I want to see what what exactly you're doing. So, it would be, useful, and for you as well as the rest to look at that example. If it hangs, then why is it hanging is something that needs to be looked at. Okay. But there are, yes, the way that it has to be used has to, you have to be somewhat clever in how you put this thing to use. You have to compare this thing with, random simulation versus this simulation. Okay. In real life, random simulation based test things, they are run for days, if not weeks. Okay, to cover, so the comparison should be apple to apple. Not we're saying, oh, I did one example and 16, but that may be a real issue. So scaling is an issue. Okay. But what you will have to compare is there are some things, for example, in the way that it explores in a breadth first fashion here. So just by doing 5 iterations, okay, 5 unwindings,
right,
will explore a lot more, okay, because you're doing symbolic execution. Okay, in each iteration, you're exploring for multiple input values. Okay.
Okay.
So look at the BMC formula in each iteration. That's why I keep calling it as symbolic. It's a symbolic trace. Okay, in the sense that one trace will that formula represents multiple executions, multiple actual, real executions on real inputs. Okay. So sometimes because of that, even shallow unwindings might find certain bugs, which they have found bugs which miss random simulation for, hours or weeks together. Okay.
Okay.
And I will show you one example of that. Okay. Therefore, so I'm answering your question in 2 ways. One is that shallow, just because you do, this is for certain programs. Okay. I'm not saying that this is true for all kinds of programs. For example, here, sometimes you can, even for shallow, it will explore a lot more execution traces. Okay. Even for shallow unwindings. For small values of unwind. There could be some programs where the only way you can get is things. For example, here, if I have while n, if I have n as 10 to the a million, 10 to the zillion or something like that. Okay.
Yeah.
Now, I mean, so there in this case, because I won't get out, I mean, the only way I get out is after I do so many increments on I. Okay. So that may not be so way too, so then it is useless. Okay. So for those kinds of programs, this may not work out. Okay. But suppose there are, and then so yes, it doesn't scale and find the thing for all things. Yes, for huge values of n, it does not scale. Okay. But what I'm saying is that even for shallow unwindings, because it does symbolic search of the thing, it covers a lot more than deep unwindings with simulation would in some situations, and that's why it adds value as a bug hunting tool. Okay.
So like ideally I should think of it as a tool rather than exhaustive thing which will give me all answers.
Say that again. Ideally, what did you say? Yes.
So ideally, like I should think of this as a tool in a whole kit, like not as
This is not So this, as I said, it's deliberately incomplete, and because it should be viewed as a bug hunting tool. Okay. As yes, it's one of the arms that you have in your arsenal. Okay. For doing the thing. And then if it doesn't scale, and there are ways that you can do to scale it. Okay. That is in the thing. But you're right. If your unwinding is more than in some case even a few hundreds and so on, it may you may need to it may not scale. Yeah.
Right.
And there you then after that you will have to use tricks in modeling and so on to extend to push the envelope of this thing. Yeah. And that is where all these invariant generation, etc., which is our next topic, where you will get. So there's scalable version of either model checking or a completely different one, which does explore weak invariance. Okay. To
generate the invariants automatically.
Yes.
Oh,
okay. And the first the technique that we will start looking at will be abstract interpretation, which scales for hundreds of thousands of lines of code. Okay?
Nice.
But it limits the kind of property that you can check. Big class of properties. Okay? But nonetheless, I will promise that I will show you one example where, despite this limitation of this working only for small unwindings, that it still can add value for the reason that I explained. But I will show you an example. But let's look at your example in one of the tutorials to see what's happening there. Yeah.
Correct. Yeah.
Okay.
So where do I add the example, like on Moodle or something?
If say that again, if I could.
Where do I upload the example file?
I mean, you could. What you can do is, why don't? No. In one of the tutorials, maybe starting next week. I don't think I'll start. I mean, you should, if you want to. Either you could. Present it at one of the tutorial next week, say next Thursday.
Okay.
Or if you want to, do it, send it to Diganta. Okay. And, we will review, or you can mail it to us. Or I think best thing is, even you could mail it. Okay. We can review it and then let's see what exactly is going on there. If it's a real inherent limitation that is, CBMC is hitting the wall, okay, with arrays, or there is something crazy that's going on.
Yeah, I think
But
it's
nonetheless, the point that you bring is a real issue. Okay, so there is limitations for this scaling, and all the research and other more advanced techniques are aimed towards solving those problems, the scalability issue. And a few of them we will see. Yeah.
So like this automatic invariant generation can like, does it, is it like in CMBC out of the box? Can I enable it with some option, or we need to do something more?
In CBMC, you can, there is another version of another sister tool that uses, a lot of the engines that are available in CBMC, all this SSA notation and all those things. It's called 2LS. Okay. And that is one thing. That is one, and then we may get a little bit towards the end of the course. But this abstract interpretation, yeah. So CBMC itself does not do it. What I'm saying is, if you really want to explore it, there is 2LS. There is a sister tool called 2LS. Okay. Why it is called 2LS, I don't know, but nonetheless, that generates invariance. Okay.
Like TWOLS or T2 as in number 2LS.
Yeah, it's number 2LS. Number 2LS.
Okay.
Just three letters is the name of the tool. 2LS. Okay. Yeah. But even that tool, the method that it uses, it aims for precision as opposed to efficiency and scalability. Okay. But it does generate. I think the kinds of invariant generation tools that are now becoming in practice is where you use a whole bunch of methods, including some machine learning methods, to generate approximate invariants that are not really inductive, but they're almost 90% invariance, okay, inductive invariance. And then you use CBMC-like tools to fix those approximate invariants to make them real invariance, okay?
Okay.
That hybrid method is the real promising, that can address scalability, yeah?
Right.
Any symbolic methods have limitations of this kind, unless you use abstract interpretation, okay, which searches for very weak invariance, and it has identified a sweet spot which that method works for a whole large class of properties that you normally need to that software engineers need to check, okay, regardless of what your program is doing. Yeah. So in my next thing is, first I will tell you a naive way of symbolically generating the strongest invariant, which is what model checking methods, traditional model checking methods used to do. Okay, but they don't scale. Right. And then I cover, so that theoretical foundation about how you could generate that is important to understand before we move to abstract interpretation. Yeah, but abstract interpretation is something, those ideas, they really scale. Okay, and there you have to make a compromise. Either you have to compromise, there's a trade-off in what properties that you limit the kind of properties that you want to verify, then generating weak invariance is okay. Or if you want full, I don't think you can aim for full precision, but rather go through this route of generating approximate invariance and so on. Yeah.
Okay.
Okay, good.
Yeah.
Thank you.
Thank you.
Yeah, I'll stop sharing here.